Right now, somewhere in our galaxy, a planet is orbiting its star so closely that its entire year lasts only a few days. It's a gas giant, roughly the kind of world you'd expect to find far away from its star, cold, massive, and surrounded by the darkness of the outer system. Instead, this planet is sitting almost directly in the star's furnace. Its atmosphere is being blasted by radiation. Its temperatures reach thousands of degrees, and yet the planet is still there. That sounds impossible, but the real mystery is even more interesting. How did a planet this enormous get so close to its star in the first place? Look at our solar system. Mercury, Venus, Earth, and Mars are the small rocky worlds close to the Sun. Then much farther out, we find Jupiter, Saturn, Uranus, and Neptune, the giant planets. For a long time, this seemed logical. Young stars are surrounded by disks of gas and dust. Close to the star, temperatures are hot. Farther out, things become cold enough for ice and other solid materials to accumulate, helping giant planetary cores grow. So the basic expectation was simple. Rocky planets close, gas giants far away. Then astronomers started finding something completely different. Hot Jupiters. Jupiter-sized planets hugging their stars in unbelievably tight orbits. Some complete a year in only a few days, and some in less than a day. NASA describes hot Jupiters as giant planets orbiting extremely close to their stars, with temperatures reaching thousands of degrees. Our solar system has nothing like them. And that forced scientists to ask a very uncomfortable question. Did we misunderstand how giant planets get made? Imagine standing on a world like this. Actually, you couldn't. There is no solid surface waiting for you. It's a giant atmosphere of hydrogen and helium, heated by a star millions of kilometers away. On the hottest hot Jupiters, temperatures can climb above 3,000 degrees Fahrenheit, hot enough for metals to exist as vapor in the atmosphere. The star doesn't just illuminate the planet, it dominates it. Radiation pours into the atmosphere. The upper layers can expand, and some hot Jupiters are losing material directly into space. So now we have a planet that is not only extremely close to its star, it's also being slowly changed by that proximity, which brings us to the biggest mystery. Why is it there at all? One possibility is that the planet didn't form there, and this is where things get fascinating. Maybe it was born much farther from the star, out beyond the region where ice and solid material could help a giant planetary core grow. Then, during the chaotic early history of the system, something changed. The planet began moving inward, slowly. Millions of years could pass, and the planet kept moving closer. This process is called planetary migration. Scientists have several ideas for how it could happen, including interactions between a giant planet and the disk of gas and dust surrounding a young star, or gravitational interactions with other planets. Eventually, the planet could end up exactly where we find it today, dangerously close to its star. But that creates another problem. If a planet spends millions or billions of years this close to a star, how much of its atmosphere should it lose? We know atmospheric escape happens. Astronomers have observed hot exoplanets where intense stellar radiation is stripping material from their upper atmospheres. In extreme cases, the planet can even appear to be slowly evaporating. NASA's observations of Kelt 9b, for example, show just how violent the environment around an ultra-hot Jupiter can become. But here's the important part. Not every hot Jupiter behaves the same way. Their masses are different, their stars are different, their ages are different, their atmospheres are different, and their magnetic fields and internal structures may also matter. So scientists aren't simply asking, why hasn't this planet been destroyed? They're asking something much more interesting. How do planets survive and evolve under conditions this extreme? And that's where these strange worlds become incredibly useful, because hot Jupiters aren't just weird planets. They're natural laboratories. We can't recreate a Jupiter-sized world next to a star here on Earth. We can't watch a planet evolve over billions of years, but the universe has already built the experiment for us. And every extreme planet gives astronomers another test. Different temperature, different orbit, different mass, different atmosphere. By comparing them, scientists can figure out which models actually survive contact with reality. And that's important because our first assumptions about other solar systems turned out to be badly incomplete. After thousands of exoplanet discoveries, we now know planetary systems can look radically different from our own. The universe wasn't wrong. our expectations were. And that's the part I find most disturbing. For most of human history, we had no idea whether planets around other stars even existed. Then we built better telescopes, and suddenly, the universe started showing us worlds that didn't fit the picture in our heads. Hot Jupiters, super-Earths, mini-Neptunes, worlds being torn apart by their stars. Worlds unlike anything in our own solar system. And we're still at the beginning. Because every time we find something strange, we have to ask whether it's an exception or evidence that our understanding is still incomplete. So no, this planet isn't breaking the laws of physics. It's doing something more valuable. It's forcing us to test those laws against a universe far stranger than the one we imagine. Because the most dangerous assumption in science isn't saying, we don't know. It's believing we already know. And somewhere out there, right now, another planet may be doing something even stranger. Something our models haven't predicted. Something our telescopes haven't found yet. If you want to explore the planets that are forcing astronomers to rethink what a world can actually be, subscribe to Xplore Unknown. Because the strangest discoveries aren't the ones that confirm what we know. They're the ones that make us question it.